Hello and welcome to the fourth and final part of our presentation on microwave passive components. Myself Sanjit Kumar Singh, lecturer in Electronics and Telecommunication Department at Praveen Patil College of Diploma Engineering and Technology. In this presentation, we cover the directional couplers, and particularly the two-hole directional coupler, its working principle, applications, and the parameters like directivity, coupling factor, and isolation. And then we go for the basic microwave antennas, particularly the horn antenna and the dish antennas. So moving on, the unit outcomes. The unit outcomes, of course, is to describe with the relevant sketches the operation and the working principle of the given microwave passive component, and how to set up the microwave test bench, and to explain the functions of the given parameters for a directional coupler. And overall course outcome expected from this unit is to maintain passive microwave components and devices. So first, the directional couplers. The directional couplers, particularly the two-hole directional coupler, is covered in this presentation. So let's see for what it is used. So directional coupler waveguide are used in unidirectional power flow measurement. It can be used for standing wave ratio measurement and unidirectional wave radiation in reflectometers. So what should be the whole distance between the two? So this hole between the main waveguide and the secondary waveguide has to be twice n plus 1, that is odd number multiple of lambda p by 4, that is quarter wavelength. So odd number of quarter wavelength distance of separation should be there between the bores or the holes in the main waveguide, where n is equal to 0 or any positive integer, and different sort of attenuator is used to absorb backward wave components. So we see that at port 3 there is a matching resistive termination that absorbs any backward reflections. So when a fraction of wave energy and is entering into the port 1, it will pass through the holes, through the gaps, and is radiated into the secondary waveguide, as the holes act as slot antennas. So the holes itself with the small segment of the waveguide acts as slot antennas. So the forward wave in the secondary guide are in the same phase regardless of the hole space, and are added at port 4, and any backward waves in the secondary waveguides are progressing from right to left, are out of phase and cancel out at port 3. Still, if some waves remain, that is absorbed by the matching termination resistive element used at port 3. So in a directional coupler, all 4 ports are properly matched. So what are the parameters of a directional coupler? So these are the parameters generally considered. The coupling factor first is it is a measure of ratio of power levels in the primary and the secondary lines. Hence, if the coupling factor is known, if we know how much power is coupled to primary to secondary, then a fraction of power measured at port 4, by measuring power at port 4, may be used to determine the power input at port 1. So coupling factor is given as a 10 log base 10 by P1 by P4. Then directivity is a measure of how well the forward traveling wave in the primary waveguide couples only to a specific port of the secondary waveguide. So directivity in terms of dB is given as 10 log base 10 P4 by P3. Then another parameter is isolation. So isolation on the input side, isolation on the output side are considered. So isolation is defined as the difference in signal levels in dB between the input port and the isolated port. So port 1 is isolated to port 3, and similarly for port 2, port 4 is isolated to it. So isolation in terms of dB is calculated as 10 log to the base 10 P1 by P3, where P1 is what the input power that is injected or traveling in the main waveguide, and P3 is the power output from port 3, that is backward reflected, and P4 is the power output from the port 4, that is coupled to port 4 secondary waveguide section. Then a question can be asked, which type of antennas generally we see, or one might have noticed generally there are many answers. You might have seen the Yagi-Ura antenna or the dish antennas mostly used, or to some extent the microwave antennas. Okay, so microwave antennas we are mostly concerned here. So what is basically an antenna doing? An antenna convert an electrical signal to electromagnetic wave and vice versa. Means in the receiving mode, electromagnetic wave is captured and is converted into electrical signal. So because of the line of sight transmission of the microwave signals, highly directive antennas are preferred, as they don't waste radiated power and provides more gain and directivity. So special high gain and highly directive antennas are used in microwave antennas. So there are many antennas in the microwave region operating, helical antennas, the horn antennas, the dish antennas, then bicorn antennas, phase array antennas. So there are many antennas. So here we are mostly concerned about the horn antenna and the dish antenna. So horn antenna is the most widely used. It is nothing but the flared waveguide. So flaring angle could be in the range 20 to 60 degree, and as the signal is radiated from antenna, it is radiating in 3-dimensional, remember. So even a section, a waveguide section, rectangular section with the open end can act as antenna radiating out energy, some energy, but it is inefficient because there are more losses than the gain. So what is the remedy? So for that, what we are doing, by connecting a horn at the open end of the waveguide, the abrupt discontinuity at the neck, in the adjacent figure we can see, is changed to a gradual transformation. When impedance is properly matched, then energy traveling in the waveguide is radiated with the improved directivity and reduced diffraction. Okay, so what are types of horn antenna? There are many types of horn antennas, but they can be classified into these three basics or four: the pyramidal, sectoral and conical. Or it could be case horn antenna or hog horn antenna. The case horn, these two, case horn and the hog horn antenna, are low noise antenna used in satellite and tracking system. So in the pyramidal horn antenna, what we see, the flaring is 2-dimensional. So both the electric field and the magnetic field dimension are changing. Moreover, it is truncated, means the top of the pyramid is cut and joined to the main rectangular waveguide end. So that is truncated pyramidal horn antenna. Then the second diagram we are seeing, B and C, is of sectoral horn antenna. In the first B, it is the E field horn antenna, because flaring is in E field, and in the C, it is the flaring is in H field. Then the D is the conical horn antenna, where the flaring is mad annular shape, conical shape, and E is the exponential horn antenna. So the abrupt changes at the neck or throat from the main waveguide to the flaring is reduced, the discontinuity is reduced, and hence the efficiency of exponential horn antenna is more than the rest. So moving on. So what are the different parameters that are considered for microwave antennas? A quick look at those parameters. So it is just the antenna performance is just on the antenna gain. It is just on the directivity. The directivity is what it is the maximum gain, directive gain in one particular direction. For a given direction, maximum gain obtained is the directivity. Then power gain takes into account the efficiency and the directive gain. Then bandwidth of microwave antenna is generally narrow band, but for horn antenna, since horn antennas are non-resonant antennas, so wide bandwidth is possible. Typically the bandwidth is 10% of the propagating operating frequency. So if the operating frequency is 10 gigahertz, so 10% of that will be 1 gigahertz. So 1 gigahertz bandwidth is quite large. So we can say it is quite a wide bandwidth. Beam width. Then beam width. What is this beam width? Is the angular separation between the two 3 dB points from the radiation pattern plot, and this beam width could be ranging from 10 degree to 60 degree. Then antenna resistance takes into account the radiation resistance and the losses. So radiation resistance, what is this radiation resistance? Radiation resistance is defined as the ratio of the power radiated from the antenna to the square of the current feed at the feed point of the antenna. It is also radiation resistance is also the equivalent resistance that will dissipate the same amount of power as the antenna does. And the antenna efficiency is defined as the total radiated power P out to P in at the feed point, or it is also calculated in terms of the radiation resistance as RD by the total resistance R plus RD, where RD is the lump resistance of the different losses of the antenna. So moving on to the dish antenna. The dish antenna, mostly we have seen a parabolic antenna is an antenna that uses a parabolic reflector, a curved surface with the cross-sectional shape of a parabola to direct the radio waves. The most common form is shaped like a dish and is popularly called dish antenna, that we mostly see, or the parabolic dish. The main advantage of parabolic antenna is that it is highly directive or high directivity it has, and more gain is obtained. Its function similar to that of searchlight or flashlight reflector to a direct radio waves in a narrow beam, or receive radio waves from the one particular direction only. So parabolic antenna can be distinguished one from one another in with respect to their shapes. So first, the paraboloid or the dish. The reflector is shaped like paraboloid, truncated in a circular rim. This is the most common type. It radiates a narrow pencil-shaped beam along the axis of the dish. Then generally seen for the dish TV is the offset feed parabolic antenna. The reflector is a asymmetrical segment of the paraboloid, so the focus and the feed antenna are located to one side of the dish, as we can see in the second diagram of axis or offset feed. Then cascade antenna, the feed is located, as we can see, on or behind the dish and radiates forward, illuminating a convex hyperboloidal secondary reflector at the focus of the dish. So there is a secondary convex reflector used in the cascade, and if the convex reflector is replaced with concave, then it is called Gregorian parabolic antenna. So this antenna consists of an active element, the feed, and a passive element, the dish. So it uses simple principle of reflection. The parabolic dish reflects the signal to the focal point where the feed is placed or located. LNBC is the main component in the feed horn, and it is a low noise block down converter that converts the high downlink frequency radio waves to a lower frequency electrical signals so as to send it to coaxial cables connected to TV. So applications, what are the applications of this antenna? Small dishes are, as usually seen, is used for the TV receiver, DTH service, and larger dish antennas are used for satellite communication, and then more powerful dish antennas with larger diameter of the reflector are used for space vehicles and deep space probes or research works, and for the weather forecasting and all that. So at last, here we have the summary of what we learned in this presentation. First, the two-hole directional coupler. The two-hole directional couplers are being used in unidirectional power flow measurement, SWR, standing wave ratio measurement, unidirectional wave radiation. But the requirement, remember, is between the two holes should be separated by odd number of quarter wavelength of the signal that will be propagating in the main waveguide. Then we also saw the some of the parameters, important parameters of the two-hole directional coupler. These are the coupling factor, how much of the energy is coupled to a particular port, desired port. Then directivity is how much it is ratio of how much the energy is forwarded in the desired direction to that of the backward direction. Then isolation between the two ports, particularly the port 1 and port 3 near about on the input side, and port 4 is isolated from the port 2. These are the important parameters of the directional hole coupler. Then we saw the horn antennas by connecting a horn at the open end of a waveguide, the abrupt discontinuity or abnormality is changed to a gradual transformation. So that is more efficient in case of the exponential horn than the pyramidal or the sectoral horn antennas. Then we also saw the dish antenna or the parabolic dish, different types of it. The most commonly used offset feed for the dish TV. So a parabolic antenna is an antenna that uses a parabolic reflector with a curved surface with the cross-sectional shape of the parabola to direct the radio waves to and from the feed point of feed horn. And then the offset feed, we saw the reflector is an asymmetrical segment of a paraboloid. So the focus and the feed antenna are located to one side of the dish. So for more deeper learning, one can go through the learning resources given and the websites. Thank you very much.